Good afternoon, everyone, and welcome to your AP Physics 2 live stream. Welcome to Prep Week Day 4. That should say 4, not 2. Today we'll be looking at the questions that we did yesterday. We'll be talking a little bit about question 1 and going through those solutions. I'll be tackling question 1. Mr. Eaton will be tackling question 2. And then we'll give you some more advice on the AP exam and a preview of what's coming tomorrow. I'm Joe Mancino from Glastonbury High School in Glastonbury, Connecticut.
And I'm Brendan Eaton from Reedy High School in Frisco, Texas. Mr. Mancino, take it away with question 1.
Well, I first need to say thank you to everyone who emailed me their work on questions 1 and 2 from yesterday. I've tried to respond to everyone. I think there was one person who is still giving me access to something that they had typed in Google, and I just saw those emails. So thank you. I will get back to you. But thanks to everyone who reached out, and even those of you who just said thank you. There is one student who said that they have watched our videos more than anything else in the last week, more than any TV shows or movies. And I mean, I hope this is helpful. That sounds like kind of a boring week, but I hope it's been helpful. I hope it's been super useful, and you can catch up on some TV and get your binge watching in next week. So thank you to that student. All right, here comes question number 1. Question number 1 was about thermodynamics. It was about gases that were inside some containers. Information kind of nested in the text of this question that you had to be a bit of a careful reader to figure out. So these cylindrical containers have samples of monatomic ideal gas, each fitted with a movable piston of negligible mass. The pistons are labeled right there. Each sample of ideal gas has the same volume and the same number of moles. Now, having the same volume and same number of moles was a clue that you had to read. Reading carefully is going to be really important on this test. The AP Physics 2 Development Committee is telling you everything that you need to know on this test, but you have to read real carefully. The cylinder on the left has diameter d, and the cylinder on the right has diameter 2d. Now, earlier, when we were talking about the idea of continuity of fluid flow, Mr. Eaton and I let you know that sometimes the College Board will tell you about the ratio between diameters when you really need to know the ratio between the areas. Now, in this case, the gas on the right is in a container with double the diameter, but double the diameter means 4 times the area. All right, on the top of each piston is a mass. Both samples have been in the same room for a long time. Now, I didn't type that they were at the same temperature, but in the responses that I read, I think a lot of you caught that as a clue for they're at the same temperature. All right, which container, if either, is in which container is the pressure greater? Well, a lot of you picked up on both containers have the same value for volume, number of moles, and temperature, so that the pressure is equal in both containers. So that was awesome. Those of you who wrote really good responses to that made a reference to the ideal gas law and pointed out that the pressure was the same in both containers, even caught on that the temperature was the same. So nice job there. Which mass is greater? Well, this took a little bit of doing. Somewhere in your justification, I really was hoping to see something about the relationship between pressure, force, and area. So something like, pressure is force divided by area, or P equals F/A, or because the pressures are the same, the ratio of force and area is the same. And that would tell you that because the area of the piston on the right is 4 times as much, the weight on top of the piston on the right is 4 times as much. 4 times the force over 4 times the area, that is the same pressure. All right, And then we had to talk about how this equation matched the answers that you were talking about, specifically how the variables in that fraction relate to the weight on top of the actual container. So the specific variables I was hoping that you would bring up were the, pardon me, I need to cough. Thank you. Were the diameter of the container, the D variable, and F, the force that the gas exerts against the bottom of the piston. And that's what I said F was. So there should have been some mention of that the force exerted upwards against the bottom of the piston equals the force exerted downwards by the weight, either implicitly or explicitly, some way that you equated those two things. And also that you referenced that the container with a larger value for the diameter needed a greater force, and that the temperature and volume and number of moles were equal. So if you said all of that and talked about the variables in this equation and how this equation matched your reasoning in question part B, then give yourself the credit for that. Nice job. This is the heart of what a qualitative quantitative question is. Can you take an equation and match that to a verbal description that you've written? Okay, then I presented you with a PV diagram, and your job was to look at this diagram and interpret what some students said. So leave the diagram up here for just a second, and then we'll click to what the students said. The diagram will come up again in just a moment. One of the things to note is that the final pressure is 1/3 of the initial pressure, and the final volume is 3 times the initial volume. All right, so process A is the dotted line, process B is the curve. Student 1 says the gas does more work in process A, which means a greater change in the internal energy. Doing more work requires more heat energy, so the gas would also absorb more heat energy during process 2. Sorry, that should have said process A. Student 2 says the change in internal energy is the same for both processes. So the amount of energy transferred to each gas must also be the same. Now, each student said at least one right thing and at least one thing that needs some tweaking. So let's take a look at what those things were. First off, I was really hoping that in your responses, you would discuss which process, either A or B, does more work. So first off, let's take a look at the work done by process A. Process A, denoted by the dotted line, does an amount of work equal to the area between that line and the x-axis. So the area shaded in blue is equal to the work done as the piston expands in process A. The work done in process B is equal to that area, the area under that curve. So clearly more work is done by the gas in process A. So if you said, let me click back here, if you said student 1 is correct because more work is done in process A, you were right. All right, click forward here. Then there was the question about the change in internal energy. There were some correct and incorrect statements made about that. But the change in internal energy is independent of the processes. So I'm going to take away information about the processes, the way that we get from point I to point F, and we're just going to look at point I and point F. The change in internal energy, whatever it is the same for both processes, because you can get all the information you need about the internal energy of an ideal gas from just knowing the information at one point, regardless of the changes that happen to the gas between I and F. The internal energy is related to the temperature of the gas. Well, the temperature of the gas is the unique combination of P, V, and N. And that's the same at either of the regardless of how the gas gets from point I to point F. The internal energy at point F is the internal energy at point F, regardless of the path. So the change in internal energy is the same for both of those. And because of the specific way I set this up, PV is the same value for both of those points. Remember, the temperature of a sample of gas is PV divided by NR. Well, those PV values are the same. It's either P1 times V1 or 1/3 of P1 times 3 V1. That was an isothermal process. So those of you who pointed out that student 2 says the change in internal energy is the same, nice job. And those who pointed out that student 1 was incorrect to say a greater change in internal energy for process A. That was also, you correctly identified their incorrect statement. But now we get to the discussion of which gas absorbs more heat. And that was a more subtle argument involving the first law of thermodynamics and the conservation of energy. So those of you who argued specifically based on the amount of work done in this eventually in this process that ends up at the same temperature at which it started, and said that definitely for process one, for process A, there is definitely more heat energy added because there's more work done and there's no change in the internal energy. You were absolutely correct. So student 2 is incorrect. The amount of heat energy is different that's added to each gas. For process A, there's more heat energy added to the gas because process A does more work and the gases have the same internal energy at the beginning as they do at the end. So any work done either in process A or process B is fueled by the addition of heat. All right. The next part of this question involved thermal conductivity. There are two bars that are connected, bar A and bar B, metal A and metal B. They have the same cross-sectional area, but they're made of different materials. Well, remember, what goes in must come out. Energy is conserved. Metal A, the bar made of metal A, is absorbing thermal energy from whatever hot thing is keeping that side at 100 degrees Celsius. Metal B, bar B, is putting heat energy in whatever is keeping the right edge of it at 20 degrees Celsius. So if you were to just draw arrows showing the flow of energy, there's energy going into the bar because of a temperature difference on the left, and energy leaving the bar because of a temperature difference on the right. But this bar has reached steady state. They've been like this a while. So the net flow of energy is zero. Energy in equals energy out. That means the rate of heat exchange, the rate of heat flow, is the same. Thermal energy flows at the same rate through both bars. Well, a couple lessons ago, you saw this equation. The rate of heat flow, Q over delta T, the number of joules per second of heat energy, depends on thermal conductivity, cross-sectional area, change in temperature, and length. Now, that's a lot, but a lot of those things are the same for each bar. So one way to look at it is this. My first approach is mathematical. My second one is not. As this test, this AP test this year involves a lot of typing and a lot of explaining and not a lot of equations, you can go at this one of two ways. You could say the energy flow through metal A equals the energy flow through metal B. Or I just rewrote the thermal conductivity equation with those little A subscripts, and then I wrote it again with the B subscripts. So the heat energy per second for bar A equals the heat energy per second for bar B. And then I put those two things equal and I crossed out the areas because those are the same on both sides. I crossed out the L's because those are the same on both sides. And what we're left with is this relationship. The thermal conductivity of bar A times the change in temperature for bar A equals the thermal conductivity of bar B times the change in temperature of bar B. Well, we know the changes in temperature. The change in temperature for bar A is quite small. The change in temperature for bar B is comparatively large, which means that the thermal conductivity of bar A has to be high, and the thermal conductivity of bar B has to be small. Could you type all those things? Yeah, you probably could. If you really wanted to type what I have here as subscripts, just don't leave it as a subscript. If you write KA, the readers will understand that. But knowing that this test involves typing, it involves words, involves explaining physics in prose, explaining physics ideas without using algebra, without using calculations, I would probably write, if a metal bar is a good conductor of thermal energy, both ends of the bar will be about the same temperature. If a metal bar is not a good conductor of thermal energy, both ends can be at quite different temperatures. In this situation, I would apply that kind of thinking to what's going on with these metal bars. Material A is clearly a good conductor of heat energy because most of it is at the same temperature. The cold side of it was able to get pretty warm versus metal B, where the cold side of it is cold and the hot side of it is pretty hot. The final question was about the electric current that could run through those two bars. And I loved the answers that I saw for this. Almost everyone said the two bars are in series, so the current through them is the same. Great job on that question, folks. I really liked reading those answers. That was very encouraging. Now, some of you wrote asking, are we going to see questions like this that connect ideas across topics? If you look back through all the videos, every time Mr. Eaton and I said, and the skills we'll be working on today, most of the time we said connecting ideas across topics, linking physics ideas from all over the AP Physics 2 curriculum. You are probably going to see a question that has a diversity of physics topics. That's the beauty of this course. We apply the big ideas in physics: conservation of energy, conservation of momentum, conservation of charge, all the big ideas. We apply them in different contexts, but the physics always tells the same story. All right, here with question 2 is our very own Mr. Eaton. Take it away, sir.
All right, let's do this. Okay, question 2 was based on a circuit with a nice little capacitor inside of it. Okay, it says that the circuit shown above contains two bulbs, A and B, and an ideal battery, no internal resistance, a capacitor, C, and the switch that's initially open. The switch is eventually closed, but we're going to start talking about it being open, at least to begin with. Excuse me. So what I like to break these types of circuits down, actually just about any circuit down that has multiple switches or multiple branches, I want to know what the circuit's doing right now. I'm not even looking at the question, what it's trying to ask me, because we haven't even looked at what section A is actually asking yet. So what's the circuit doing right now? Don't look at your response, just look at what you have on the screen. Hopefully you know that bulb A and bulb B are just in series with each other, and you have, if they're identical bulbs, they have the same brightness, they have the same current, they probably also have the exact same potential difference or the voltage drop across both bulbs if they're identical. Now, what's happening with the capacitor? Since there's a switch on that branch of the circuit that has the capacitor, hopefully you know that the capacitor is doing absolutely nothing. There's no complete circuit on that side of the branch. It's basically non-existent until you actually close the switch. So what's it doing right now? I would say that bulb A and bulb B are at the same brightness, same current, same potential difference because they have the same resistance. You can say it a bunch of different ways, but I would just note that that's what it's doing at that point in time. All right. Now we know that the switch is eventually going to be closed. So you still need to think about what happens immediately after the switch is closed. So as soon as you close that switch, where does all of the current flow that's trying to go to bulb B? Yeah, that's right. It's trying to charge the capacitor as fast as it possibly can. The capacitor is just grabbing up charges as fast as it possibly can, and it's stealing all of the current from bulb B. So bulb B is not lit up at all, and bulb A is still lit up. Now, after a point in time, this is immediately after, but if I say a short period of time, what is happening over time, a short period of time, while that capacitor is charging? So we discussed in our previous lessons that as the capacitor is charging, it starts building up charges on both plates of the capacitor and it eventually becomes full. We're not at that point yet, though. I'm talking about just a couple of seconds after you close the switch, not immediately after, and not a long time once the capacitor reaches steady state. What's happening during that time? Well, the capacitor, the current to the capacitor begins to decrease over time, and the current through bulb B begins to increase over time. So what do you think is happening to the brightness of bulb B a short time after the switch is closed? Hopefully bulb B is getting a little bit brighter, a little bit brighter, a little bit brighter. And a long time later, what happens a long time later after the capacitor is fully charged? It's in steady state. Let's see the next slide. All right, after a long time, capacitor is fully charged. That's your key word to know capacitor is fully charged. That circuit goes back exactly like it was in the very beginning with the switch being open. Bulb A and bulb B will have the same brightness, and there's no charge going to the capacitor anymore. The capacitor is fully charged, and basically, like I said, it goes back to the initial state. So after, if we look at, oh, I have one more question for you. I'm sorry, I forgot to ask this. If you were to take the battery out of the circuit at that point in time, okay, imagine that the battery is not there. Take your thumb and put it on your computer screen and cover that battery up. What's going to happen if you pull the battery out and the switch is still closed and the capacitor is fully charged? So think about it for just a second. I know it's not part of the question, but I think it's important to think about. And it sounds like a really good question that could be on similar to this year's question. I have no idea what this year's test looks like, but it's good to think about. Okay, so bulb A goes out completely. Is bulb B lit up? Think about it just for a second. Okay, your thumb is probably still on the battery, and notice that bulb B just has a simple circuit with the capacitor. So the capacitor is actually discharging across bulb B, and we don't need to talk about for a long time versus a short time or anything like that. We're just strictly talking about if I momentarily take that battery out of the circuit, the switch is still closed. What does the circuit do? Talk about the behavior. Okay, now part A, we're finally at part A. So I did take, what, 2 or 3 minutes just to figure out what happens if I just change different parts of that circuit. Not a big deal. You might have time to think yourself through that before you start looking at what the individual sections of the questions are actually asking you. All right, so on the next slide, we've got section A, and it says, which of the graphs above best shows the brightness of bulb B before and after the switch is closed? So again, part of that reasoning that we went over, the immediately after the switch is closed versus short time after versus long time after, those 3 things, all of that reasoning played back in just by looking at the circuit. I did no math. I used no equations. I just simply went through the concept of what's happening inside of the circuit. So graph A, graph B, graph C, graph D, which one of these identifies with the reasoning that we've already gone over? And hopefully you picked graph A. So notice on graph A, you have a nice constant brightness, drops down when switch is closed, and after a short time, notice that you have that nice curvy line going right back up. Mr. Mancino's mocking me, going right back up to the same brightness. Perfect, I love it. All right, so part B. Part B is crazy. I'm pretty sure this came out of Mr. Mancino's mind. He just made this up. Okay, after the capacitor is
How do you
fully
know it comes out of
charged,
my mind just because it's crazy? I
you're
mean,
the only
it's
guy I
correct, but
know
still.
that would modify a capacitor while it's charged. Just sounds like a bad idea, but very interesting to think about. All right, so you have 2 identical capacitors, C1, C2. You charge both of them in the circuit. You take it out, you take capacitor C2, you move the plates further away from each other. Now, before we go any further reading this, I want to say something. What do the plates want to do? Well, they're oppositely charged, they're attracted to each other. So if you are physically pulling the two plates away from each other, are you doing work on the system? And the answer is yes. So if you're doing work on the system, you're probably changing some sort of energy. I'm not approaching this with energy, but you could have done that. And I'll talk about how that fits in just a second. All right, so in a clear, coherent paragraph length response, explain which capacitor C1, C2, when used in the circuit below, would cause the bulb to be brighter immediately after the switch is closed. So here's the first thing to think about. Initially, when both capacitors are fully charged, what needs to be true? So I think that the potential difference across that circuit is going to be the same for both of the capacitors. And the capacitance is the same for both capacitors. Now this is before they're removed from the circuit, and capacitor 2 has not been stretched yet, or the plates haven't been pulled further apart. So if they have the same delta V and they have the same capacitance, that means that the charge was the same. So as long as we know that charge is same, we're going to carry that forwards to when you have stretched the capacitor on the next slide. So now you take C2, you take it out, D is doubled. What changes? Here's your formula chart stuff. I don't really like looking at them. There's capacitance. There's delta V. Okay, but they can be important as part of your response. It's going to be tough to type these things, but if you need to, go for it. But this is the way that I use it. I'm going to explain it to you. Okay, on the capacitance equation on the left-hand side, just looking at the fact that you're moving the plates further apart from each other, which one of those variables is changing? And hopefully you identified that D is changing. So D is being multiplied by 2 in this case. If we could click forward one time. There we go, cool. All right, since that's on the bottom of the fraction and nothing else is changing, the area of the plates is not changing, and K and epsilon naught are not changing either. So what happens to capacitance? Capacitance must be multiplied by 1/2 because distance is doubled between them. So knowing that capacitance is 1/2, oh, can you go back one? There we go. Look at your right-hand equation. Since capacitance is 1/2 as much, and we already identified that Q is the same on both of the capacitors, that means that the potential difference on capacitor C2 is multiplied by 2 as well. All right, now when you put it back in the circuit, what's going to happen? So in order to determine what's going to happen, we know that the capacitance is 1/2 as much as it was before, and the potential difference is also double what it was before. All right, this leads me to another set of equations that you'll find on your formula chart. This is all about the potential energy stored in a capacitor. So using either one of these, you should be able to identify that your energy is increasing as well. And remember, before we got into section A or into section B, I did identify the fact that you are having to do work to separate those two plates because they're attracted to each other. All right, let's take a look at what we have next. So now I know potential energy is increasing, and we know that delta V is increasing as well. What's going to happen to current? Because really, what are we trying to figure out here? We want to know, is the bulb going to be brighter immediately after the switch is closed, or is it dimmer when you put C1 and C2 back in the circuit? Actually, we're just putting C2 back in the circuit. That's all we care about, because putting C1 into the circuit doesn't change anything. So what's your current going to do? Well, your resistance across that bulb is still the same, and you know delta V has increased. So according to Ohm's law, that means that my current has to have increased as well. Now, you still need to talk about brightness. When you see brightness, you have to think power. And if you use V squared over R, you know that V is increasing, R is the same, so power has to increase as well. Now notice again, guys, at no point did we use any numbers whatsoever. We just simply looked at the fact of, well, is it going to increase or decrease? At one point, I did use a 2, and that's only because I knew the distance was increasing by a factor of 2. But as I got halfway through this problem, I just quit using numbers altogether. And I said, well, clearly looking at that equation, if delta V is increasing, then I has to increase. And if delta V increases, power has to increase as well. Therefore, the bulb would be brighter if you insert capacitor 2 back into the circuit. And what is this all in effect from? It's all because you did work on the system by separating those two plates. All right, here's the very last little question for you.
I'm gonna hit pause on that as I can see the next slide coming, and we have a crucial mistake on this slide that I may not want to put up. We can banter about that later. So one of the big things I know that you're wondering is because a lot of you focused on answering this question verbally and without equations. Now, Mr. Eaton's job was to take it equation wise, and my job is to go at it. You know, I'm on the P1 development committee. I think in terms of force and work and energy, and I think of this question two ways that I think I would just answer verbally. When that capacitor is separated, positive work is done and stored in the electric field. We're applying a force in the direction of motion, so that capacitor stores more potential energy. So that's one way that I might look at it. That potential energy becomes, that work becomes electric potential energy, becomes light. So it makes the light bulb brighter. Or you may look at it this way. Doing that change to capacitor 2, separating the plates further, increasing the separation distance, increases the potential. All right, you can make that argument even without directly referencing the equation. At a greater distance, we are going to increase the potential because of the negative sign in that calculation. So we're storing more potential, which is just potential energy per charge. We have the same amount of charge because the capacitor has been disconnected. So if the same amount of charge has more potential energy per charge, then every individual charge that runs through that light bulb is going to give that light bulb more energy and make it brighter. So you could discuss this problem either in terms of the ratios of the capacitance as you stretch that capacitor out further. It has half the capacitance, so it needs so there's double the voltage to store the same amount of charge, and then go at it with Ohm's law, I equals delta V over R, and that's fine. That's perfectly good. That's a very valid way of doing it. You could discuss power being V squared over R, also fine. Or you can separately from how you would approach it equation-wise, say, moving the plates further apart increases the potential difference, which measures the difference in potential energy per charge. So every charge that leaves every electron that leaves the negative plate of the capacitor and gives its energy to that light bulb gives off more energy for capacitor 2 than it would for capacitor 1. Even though they've both separated the same amount of charge, capacitor 2 has them separated at higher potential or higher potential energy per charge. So both of those are completely valid ways of getting there. You're not locked into using either, you're not locked into only using algebra or only using words, but I suspect it would be easier to for some of you to explain it in terms of algebra and for some of you to explain it in terms of words. You have your choice of how you explain this. That's the beauty of the AP Physics course. For those of you who are English math bilingual, you have two great ways to explain something. Those of you who prefer to focus more on the math or those of you who prefer to focus more on the words, that's fine. On a test that involves a lot of typing, definitely decide which of those you want to use. You can certainly supplement one with the other. Okay. Tomorrow we'll have some special guests as well as some final advice from Mr. Eaton and from me. If you have any burning questions, things that you need to know about AP Physics 2, about the exam, anything you feel we have not addressed, any questions that you would like us to mention on the video tomorrow, please send me an email, send Mr. Eaton an email. We're both really easy to find at our respective schools. I'm at Glastonbury High School. Mr. Eaton's at Reedy High School. We're both extremely easy to find. So send us any questions you have. We'll have some special guests tomorrow. As always, thank you very much for watching. This has been an amazing experience for both of us. Please come back tomorrow and join us for our final AP Physics live stream.
It's going to be amazing. See you all tomorrow.